Hold that for a sec.
Yeah. We have final presentations till 6 on that day.
Until 6
Yeah.
it starts.
So can we start at 6 instead of
Yeah, we can start 7. I'm saying for you guys to not be here until midnight. Up to you guys. I don't care because I'm going to speak here. You guys are going to write the answer question. For me, I'll play with my phone until the time is over. Okay, whatever. How many of you have problem with the 6 p.m., 5 p.m.? 3 of you, okay. So, what presentation is it? Alright, if you like, for example, if you like my presentation, we're going to start 9 a.m., right? Instead of, you saw the update almost, and so you can come earlier. You don't have to be there for 3-4 hours. You could be there for 20 minutes, present, and go. What kind of presentation you guys have? Is it the
RFICs?
No, I know, but I'm saying, is it like my class, or is not everybody has to be there for that class?
Everyone needs to be there. Yeah.
Okay, so we don't have a choice. We start 6 p.m. 6 is okay? Are you sure? I don't want to complain later, Okay, 6, okay. We'll start 6 p.m. And we'll start 6 p.m. So, 7. Please be here 6 p.m. I'll send the email also in the class to let everybody know.
What about Friday?
No, exam is Thursday, right?
Yeah, Thursday.
Thursday, 6 p.m. instead of 7 p.m. Presentation will be 9 a.m. I think you scheduled already with Arno. We have like a 15 to 20 minutes, to present and I'll ask questions. And I think we have about 11 group, I'm sure 12 group. You don't have to be there for all the presentation, but you're very welcome to come and sit down and listen to it, if you want, but you have to be there for your presentation. So the exam, the presentation, and I'm not sure, do we have anything else? Okay. I'm surprised in the final week, still they have a presentation in the final week.
We had our final today instead.
Huh?
They switched it. We had our final today, the presentation's on.
Okay, yeah. Here, I want to go over this paper again. This is a little bit old. I think it's from 2006, you can see. It's from 2006. But this is from Toyota. I want you to see what there is in the Prius. Or if you have seen Lexus, it said 400H, now there are 450H, They are a little bit old. They have a new model, Just you see what is inside those, cars and how do they work, We'll go over this one and we'll review a little bit more of the other things, and as I said, you are done for today. You don't have that much to go over it. I upload the exam sample, Friday, Saturday, because I need to write the solution for that. I don't have the solution, and I'll do it over the weekend, and you will have it definitely over the weekend. Hopefully by maximum Saturday afternoon you will have it. So these are the different cars they have, but look at here. This is what is happening inside this hybrid car. Look at here. All of them, they have battery, right? The battery is here. And this green line, it says these are the electrical power path. The red one, they are mechanical power path. If you look at the internal combustion machine, they don't have this one. They have a internal combustion engine, and they transfer power to the back wheels, or I don't know, or front wheels, whatever, based on whatever they are. All-wheel drive, I don't know, front wheel drive, whatever, or I don't know, maybe they have a back wheel drive also. So it's like this, the internal combustion engine. Now, when you have a hybrid electric car, see, there are two parts. There is a motor and there is a generator. These are like a coupling, It's a power split device. It's somehow to couple this generator here and this motor. Let's forget generator for now. The problem with the hybrid electric, in general, with all this internal combustion engine, can you guess what's the efficiency of this car at the best case?
35%.
I think even it's less than that. Yeah, I read about 27%, 30% top, something. But they are different. Nowadays, they are getting more efficient. They are getting better and better. Even with those ones, they are only consuming the fuel. But overall, I think it's about 30%, the best efficiency rate. And do you know how much is the efficiency when they start? Then they're going to go from 0 speed and start up? 15%. I think they are less than 10% efficient. Yeah, think about it, I'm saying I think because I don't want to say for sure, but I'm sure they are really bad in the efficiency, 10% means of that fuel inside the car, they burn it. They do all the things. They get only 10% of the energy. See? Now, and maybe most of you may have here, when you buy a hybrid car, they say save this much. They say the MPG, for example, inside the city is, I don't know, 45, 60, 50, whatever. But highway, not that much different from sometimes it is worse than the internal combustion engine. You know why?
Yeah, it's because they're...
Motor's not very efficient at higher speed?
The thing is, they don't use this one in the highway. I'm saying this is not designed for a highway. This one is going to help you when you stop. You have those low efficiencies. What you do, you bring this electric motor here to help this engine to rotate the car. And this time, the electrical path, maybe the efficiency is more than 90%. You know what I'm saying? More than 90% is efficient. That's the reason when you are inside the city, you have to have lots of stop-starts, This thing is going to help you, to save lots of fuel, get a very good MPG, but when you go to the highway, no, not that much, Not at all, it's just this path, Unless you do the stop-start, or you go down the hill. For example, you go up the hill, now you're going down the hill instead of, braking, you can recharge your battery. You can recharge your battery, which is this path we'll talk about, So, but when you are going cruising in the highway, let's say you're going to Vegas, I don't know, mostly it's flat, when you go there. So, is your internal combustion engine you are using, right? Now, as I said, when GM had a product, they called it just a stop-start hybrid. They had one product, GM is not there anymore. They do it only when this guy is going to come in only when you start the car from 0 speed, And as soon as the speed comes to some level, for example, 20 miles per hour, 15 miles per hour, it's going to go away. It's going to be again all internal combustion engine, right? That way you're going to save energy. Still, because at the start, the efficiency is really bad. But this path is when you are going to help the motor. You are going to help this internal combustion engine, right? When you are braking or you are going down the hill, use this path. You have a generator, and this is coupled with this one, right? You start to take the power. The power direction is this way, right? It's going to come here, goes through here, goes to the battery. You charge your battery. So there are two paths: charge, discharge. Nowadays they are trying. If you look at, for example, like Tesla has only battery and one, the one motor generator set. It can go either this way or that. The motor can change the mode to become a generator, and that way they're going to save on all these kind of things. But with the conventional system, you have to have the both motor and generator. Now, so this is how. This is how a hybrid electric car works. It's all the car. There are another type of hybrid electric car. They call this one parallel. They call it parallel hybrid. There is a series hybrid. Series hybrid, if you look at Chevy Volts, is a series hybrid. You guys have seen Chevy Volts. And there was a company in Irvine. Now they are not anymore. Or maybe they came back. They called Fisker. They were kind of, branched out from Tesla, and they were suing each other with Elon Musk, over that. They say you stole my. But Fisker and the Chevy Volts, they are series hybrid car. Basically, series hybrid car, they're electric car. The way they work, they have a gas tank, right? A tank of gas, and they have a small engine. It consumes this power and generate electricity, and it charges the battery. So the battery is going to drive the system. If you look at the electric car, the pure electric car, like a Nissan Leaf or Tesla, they have a battery and they have an inverter and they have an electric motor and they drive it, right? But the series hybrid, they have all these things, plus there is a tank and a generator. They can burn this gas and recharge the battery. It's a pretty smart concept, you know, I like it, you know, because lots of people, they are explaining, you know, even in the big cities like LA or I don't know, even San Diego, if you look at how many of you guys, you know, you drive more than 60 miles a day? And not many of you, you know. There are some, still they do, you know. But when you buy Chevy Volts, I think the previous version would cover up to 45 miles. Now they are going to 50 or 55, something like that. So when you have those kind of cars, so when you are inside the city, you want to do, I don't know, whatever you want, so you get all from the battery, and you go back home, maybe you will be short 5 to 10 miles or 15 miles, you can use the gas. But maybe 80%, when you are inside the city, you are all on electric. Or if you come to university and, for example, there is somewhere you can plug in your car, you can recharge your battery, okay? So basically, you can extend your range almost to 80 miles, you know, to travel. And when you're going to go out of the city, you know, so you can use a gas tank, right? To go extended mileage. They can go 200 miles on the gas tank, you know, so, and that's kind of thing for the long distance drive. You can do that. Now, let's look at this one a little bit more. So there's a series hybrid. I'm not talking about series, but this is a parallel hybrid. So let's look at the electrical circuit, you know, what we care more about it. So this here is talking about, you know, for example, they have 500 volt DC bus, they have a 650 different versions, you know, what kind of DC bus they are using. Look at here. This is what is going to sit here under the hood. They call it the PCU, power control unit. This inside this one, there are two inverters. There are one DC to DC converter. I'll show you the circuit. Look at this one. This is from 2006. Now is this much. The thickness is 1/4. They published something about like 6-8 months ago. Think about how much it's going to be lighter, and they're using silicon carbide. This is with IGBTs and those kind of things. They changed this one now. The thickness is 1/4. You know, and believe me, Toyota is, I believe them really. They are really good because I have seen their design in power. Like, we tear down. I worked for GM 3 years, you know, and when we were there, we tear down their work and we looked at it, you know. God, you should see it. It's a piece of art if you look at it for power electronics design. How good they designed it, they packed it, wow, it was great. You know, I cannot tell you how good it was. You know. And you will be really surprised to see how good a job they have done. At the same time, not nowadays, I'm saying. I was interviewed by Tesla in before I think it was 2009. Now they're they're good. I'm not getting said, don't get me wrong, you know what I'm saying. But 2009 it was a piece of crap, believe me. Because I worked for GM, I knew what GM is doing. We were following the Toyota, and I went to the Tesla side. But after that, it was right there. Tesla was going to close the factory, but they got a good money from Mercedes. They got money from government. They picked up. Now they are doing really good job, you know. But I'm saying at the time it was really bad. You should look at the design. You can see the differences between a good design and bad design. And GM was right in the middle, you know, much better than Tesla still, but not as good as, you know, Toyota. Now, this is what inside that unit. Look at here. They have two inverters, three-phase inverter. This is what you know, what it is, right? It's connected to a generator, it's connected to a motor, and here is the battery pack, and this is a bidirectional DC to DC converter. This is a buck-boost converter. So basically, they said we need a 650 volt here, right? This is only 300 volts, right? They boost this voltage to 650 volts. They drive their motor, right? They do whatever they want. Now, if they are going downhill or they are braking, they use the generator to send the power back through here to this system.
Is there a reason why you can't just use the motor as the generator?
At that time, to be honest, I don't know exactly why, but nowadays they are trying to do that. My professor in Ohio State designed a system, a motor. It had two rotors. Two rotors, you know. One is gonna act like a motor, one is gonna act like a generator with one stator. That was what he had a patent on that one, he did that work. So basically when you are doing this kind of thing, you will have only one system. I think nowadays they have only one, I think, I'm not sure, but I think, as I said, Tesla, I think it has only one machine on there, and they have induction, not permanent magnet. But they're trying to get it up, you know, the generator because of the cost and, you know, volume and all those kind of things. But this is what is inside the hybrid electric car. See, my point is, you know, based on the knowledge you guys know, I'm not saying you can design this, but at least when you look at it, you can understand what it is, right? There's a battery here. This is a boost converter in this way, boost this voltage here. So there is a twin inverter to derive this motor and generator, right? That's all. You know what I'm saying? If you look at it from the power electronics circuit topology, B. This is what is inside the car. And that's it, you know, and I want to show you, I was going to show you to see what's inside a real product. Let me see, is there anything else? These are some efficiency, those, oh, here. See, this is how they pack that power converter, you know. They have all this kind of thing. This is the, these are the IGBTs, gate driver. These are the heat sink here, you know, they have it. This is they're all liquid cooled, you know, all this design. And they packed them, you know, there is this, you can see there were two inverters, and there is one DC to DC converter with all the DC caps and inductors, and everything is going inside one box. And this is how they stacked it up. Yeah, this is another technology you guys are doing. This is if you look at all IGBTs, these IGBTs, they are all semiconductors or switches. They are all semiconductors. And to get a high current, usually they parallel them or series them for a high voltage. They use a wire bond. They call it wire bond. There is a small wire to connect all these semiconductors together. So the new technology, they call it, instead of using wire bonds, they're using this bus bars. They say the bus bars, you know, to connect them. They call it, I think they used to call it transfer multi-packaging, you know. The advantage of this one was, I'm not sure how many of you, I forgot to bring this in. If you look at the IGBTs, or any switches, there's the one base plate, which you can get rid of the heat. The other side, usually on the substrate and those semiconductors, there's a kind of gel. You know, there's a gel on it, and they're all in the package. So you can cool it down only from one side. With this technology, they were able to, like a pancake, you know, they were able to get it out this way and that way, both. This one is very critical, you know, because it's going to help you a lot. One of the biggest problems with the hybrid electric car is the high temperature environment and how to get rid of the heat to not burn the semiconductors. With this technology, they were able to do both sides. They were able to do the both sides, you know, coating. But everything could have problems. If you look at the conventional IGBTs, it was like this. There's a semiconductor here. There's this wire bonds, you know, connecting these things together. Now what they're doing, for example, this is very simple. They are using a base plate here to do the same thing. The good thing about this one, somehow if the temperature goes up, this wire bonds, they're like a fuse. If it goes more than something, they're going to burn. And they're, but with this one, it's not going to burn. What's going to happen? It's going to explode. Because this one is this one is not going to, this one burn is better, you know, because it's a small module, but because that one can handle, you know, much higher power, so the whole package is going to explode. But no, there's lots of protection on them. But I'm saying, this one, the big advantage was to release the heat from both sides, from the top and bottom. This one only can release the heat from the bottom side. But this one has some other advantages. Another thing is the stray inductance. All these wires, they have inductance. Here you have a much less inductance. This is another advantage of this. At the time, in Lexus, they had that technology. They used to, for Lexus hybrid, they used to use that technology. I think I am done with this paper. Just I want to show you what Toyota have done on this one. And oh, look at here. This is the look at here. This is the base plate of the IGB. See, this is a very nice heat sink design. See, this is pretty complicated because you have to put it down. This is a very nice design. Lots of final elements. CFT board to to design these things to make sure they're not going to go over temperature. Now, there are a few more things I want to talk about it, and they're one more popular circuit is power factor correction. Not the one you know from the energy conversion course. Power factor correction with power electronics. I'm going to put the circuit here. Usually we have an EMI filter here. We have a full bridge diode rectifier. Rectifier. And here, for example, you have your boost converter or buck or whatever. But I'm saying now in this case I said. So from here, you know what's happening. It's a DC to DC converter, right? And from here, this EMI filter in general, you know, is when we have lots of switching here, there is some, you know, electromagnetic, you know, the waves. It's going to go back this way, which they're dangerous for the rest of the equipment. You put this filter here to block those. Very simple if you're going to think about it. Most of our electronics equipment, they have an EMI filter to make sure they're not sending back anything to the grid or another load or equipment. So when we say power factor, what do we mean? You know, if this is the VS, right? Let me put them down here. If this is a VS, right? If this is the VS, and let's say this is the IS, right? We want to see a current like this, right? This is a unity power factor, right? If we have something like this, it's a unity power factor. We want to see how we can do it with this circuit, right? So basically, if we have a sine wave here, this one practically for this case is not going to do anything. Basically, a sine wave from current is coming here, right? And this side is going to be rectified, right? It's going to be like this, right? So I need to control my current. I need to control my current here to be, if this is a VS, let me put the VS here. And this is this current. I call it I. So this is a I. If my current I here is like this, right? How about here? Here is going to be like this, right? Because this one is a rectified version of this one, right? So basically I can have a unity power factor. Now let's see how we can do that. How we can switch this switch to do that. So what we are going to do, we're going to start this way. We said, okay, sense the Vs here, Vs is going to come in. So basically Vs is like this. Let me put it there. Vs is coming. This is a signal like this, right? This is the Vs. I will rectify this. Rectify, I mean absolute value. This is a control. You know, whatever you have, you say just don't give me a negative number. Just create a signal from this one. Absolute x, for example. So this one is going to give me a signal like this, right? It's gonna. This is all inside the DSP. It's going to rectify this signal and give it to me. Now keep this one. Another thing is I want to control this voltage, right? I want to control this is a DC to DC converter. At the end of the day, I want to be able to control, I don't know, 10 volt, 20 volt, whatever, right? So I'm going to have one VREF. This is a VDC ref, right? I'm going to have a VREF. And let's call this one this is a VDC, right? VO. This is a VO, right? I sense my output voltage and compare it with my VREF. So VREF is going to go through a PI controller. Right? This one is going to make sure this one is going to follow this one, right? The controller here is going to make sure this one is following this one. Let me move this one this way. I'll bring this to whatever here it says is going to be a number. Time this one. This one is going to be my IREF. This one is going to be my IREF. IREF is this inductor, let's say IL. Right. Now I'll bring my IL. Here you can use any kind of you know. That's the IL. This one is going to be B. This is a BC. This is a B, and how this circuit, let's explain it one more time, is going to do that. Basically, this guy, all he's doing is just filtering the current here, right? So let's forget this one again, because it doesn't have any essential rule, right? We said if you're going to have a unity power factor, this current or this current should be like this, right? So what I am doing, let's say, the unity power factor doesn't care what's the magnitude here, right? The only thing is, you know, to make sure these zero crosses, they are the same, right? So what we are doing here, we are calculating the magnitude of this one. Is that how much we need here, right? But I use my Vs. Basically, the signal here you are going to see is going to be something like this as the IF, right? And the signal you're going to see here is going to be something like this. Right? Because we are generating this reference signal here, right? And this is what we have in the practice, right? So the point here is how I generated my iref. I got the domain from this loop to see how much voltage I want in my output, right? But whatever is here is a DC number. I timed it by this shape, which is the shape of the input voltage. I create my new reference for the current. Now, if my actual current is like this, if my control works good, my actual current is going to be like this, right? So which means this current is in the same phase with this voltage, right? So this is a simple, application. They use this one a lot in these power supplies and this kind of thing. They use this one a lot. This is with the power factor correction. This is the power supply. It could be simply a power supply. Look at here. This is the AC, right? And here is the DC, right? This one, for example, you plug into your lab. So you don't have to do the power factor correction, but you are going to get more power, going through the power supply to everything. This way, you minimize the power going to the load. This is one simple application of power electronics. This is the power factor correction for the DC to DC converters. How you can do the power factor correction with a DC to DC converter. See, that's, if it's like inverter we had, you know that. You say ID ref 0, right? Q would be 0, and you're going to have unity power factor, right? But this is DC to DC converter. See, it's a little bit different. How to correct the power factor. This is circuit for the power factor correction. Another big application of the power converters is a UPS system. Let me see how a UPS works. If you look at a UPS system, it's like this. UPS is not United States Post what? United Personal Services only? Partial service. This is the uninterruptible power supply, by the way. It's not that UPS, everybody knows about it. Uninterruptible power supply means, you have a load, this load is important for you, you don't want to lose the power, no way. Again, the loads, they have different type of loads. For example, it could be a very important computer, for example, keeping everything, so even you don't want to lose the power for 1 second or maybe even half a second, because you're going to lose lots of data. Or maybe it's for example, emergency light here. That's fine. If there's a flicker, it's not that big deal, like you got really nice stays off for 2 seconds and come back, Because to make it, really uninterruptible, you have to pay more for it. You know what I'm saying? That's the how much the load is important is going to define that. How much delay you are going to have. But general UPS systems are like this. And AC to DC, usually they use it show it this way. AC to DC, also this is a symbol for the AC to DC. This is like rectifier, if you saw somewhere. This one comes here, and they have a battery usually here. This is the battery unit here. You charge your battery, and you have a DC to AC. What we call this one, DC to AC? That's the inverter, right? That's the inverter. And this guy, they come both here. Usually they use a solid state switches. Yeah, you can remember this one, right? From power electronics 1. We had this one. This one can act like an AC switch, right? They call it solid state relays now. And here is a load. Now let's see how this one does work. This is a very simple UPS system, but very efficient. They call this one the bypass path. It's a bypass. if the electricity is there, this one is off. If the electricity is there, this one is off, and you send the power through here over there. Why? So you have less loss, right? As soon as you go through this path, there's a loss here, there's a loss here, right? But this way, no loss, right? You can go down. Now, another thing is, when the electricity is there, you charge your battery to make sure your battery is fully charged, right? As soon as the electricity is gone, here is disconnected, somehow the electricity doesn't exist anymore. This one, these are like this. If you are going to show them logic-wise, it's going to be like this. They have an interlock like this, you know. This one is closed, this one is closed, this one is open, right? As soon as you open this one is going to close, right? Their interlock is like this, you know. So this is a very simple controller. You do this one, you know. And you start to support the load here. Still, here, see that's the point here. Still, could be some delay. Where? Yeah, to turn off this one and turn on this one, right? There is a project where we sent a proposal. They want to have this one all the time on also. They want that option, even when the grid is there. Why? Because this is like inverter paralleling with the grid, right? Don't send any power, you know, when it's, but there is no switch. Still there is a switch. You have to have a switch, you know. But this switch is all the time on, all the time on. If by any chance this one is gone, this is there. There is no transition to say, hey, the grid went off, now we need to bring the inverter in, you know what I'm saying? The inverter is all the time there. But there is a cost for that, right? Because this guy has to be operational all the time, right? So you're paying for the loss here. You know what I'm saying? So this is a cost you pay for to have a really non-interruptible, you know, power supply. You know what I'm saying? So you have to keep this one running to make sure this is, you know, at any time you're going to have power for this one. An old system on the interruptible power supply, there was diesel generators, right? As soon as the power is off, they bring the diesel in, right? Again, there was an option, you know, for the diesel generator. This is old time, maybe 30 years ago when they had this kind of. You could have, if you don't want, because diesel, to bring the diesel in is going to take time. It maybe take like 2-3 minutes, you know, to bring it in. But what they could do, you know, for example, they had the source here, and they had a diesel here, right? If it was important, and the load is here, right? This diesel was running but not providing any power. This is like a car, you know, idling. This is standing at a point, but it's ready to go. As soon as, you know, this one is not there, this one is going to start. But nowadays we don't use a diesel. This is still lots of, you know, power consuming of energy, you know, power consumption. This one is much better, but still, if this one is all the time operational, we're going to get a little bit hit by efficiency, maybe 4 or 5%. Because this is about 98%, another 98%. Time by the charger is going to be about 96%, right? This is the UPS. This is another application, you know, people they use a lot in power electronics and control. The last thing I want to talk about is the DC motors. Now I want to talk about the DC motors and done. You know, how we can control DC motors. I don't talk about AC motors, but I want to talk about DC motor control. Very simple things, you know, and because I have seen some of you guys, you know, you work on that on some of your projects. Lots of you had the energy conversion course, but quickly I go over the DC motors, you know, very simple. There's a few equations you need to know about the DC motor, and we'll talk about it. For example, this is how we represent the DC motor. They call this one armature. Armature is the rotating part in the DC motor, and this is the inductance of the armature, LA. This is the resistance of the armature, and this is the back EMF in the armature. It could be the generator or motor. And this is the terminal voltage. And usually they have excitation system. Excitation system is like to generate magnet, to have a magnet in the system. So they call this one VF, this is the IF, and this is the LF. And this is the, if it's a motor, it's the IA like this. So equation for this one is, if you want to see for the lead, for DC motor, VT is equal to RAIA plus LADIA over DT plus EA. That one I am not going to talk about the excitation system, but another equation is very important. See, this is a DC motor, right? This one is rotating, right? If it's a motor, there is a mechanical load, right? What's the mechanical equation? T electrical minus T mechanical is going to be J d omega m over d, right? There is a rotor here, and this one there is going to be T electrical, and there is a omega m. So in the motor, electrical torque rotates the machine. Basically, T electrical has the same direction as the speed, right? And the mechanical load is going to always stop the motor, right? So you can write a simple mechanical equation like this. I assume there is no friction and those kind of things. Now, we want to control, for example, the speed of this machine, right? We want to control the speed of this machine. Let's use this one, for example, this circuit. The H bridge we had in the power electronics one. Yes. So if we have this circuit, let's call this one S1, S3, S2, S4, right? S1 and S3, they're complementary, right? So we are going to have an S1, S4 on, so this is the VDC, and this is the V out. Let's call it V out. How much is the V out? VDC, right? And S2 and S3 on, it's going to be V out, it's going to be how much? Minus VDC. So basically, if you plot the VDC, V out, it's going to be like this. This is the VDC, and this is the minus VDC, right? Let's call this one duty cycle. D, T, and this is the T, right? How much is the average voltage of this V out? V out average is this area, right? Minus this area, right? How much is that area is VDC times dt minus. How much is the area? 1 minus d t times VDC, right? Over t, right? Let's get the t here. So it's going to be VDC times 2d minus 1, right? So basically with this circuit, easily I can change the average output voltage, right? Now let's sorry, equation I put it here. Let's bring this one here and connect it to this DC machine, right? I think some of you already have done this one in one of your projects. I'm not sure how much you know. Did anyone of you did this one? Because I saw before people they are working with this kind of HPs, you know, to run the DC motor or something like that. Well, let's see how a variable voltage is going to help us to control the speed here. E is K flux omega, right? Flux is what is generated by here. Omega is the speed, and K is the constant number. in a steady state, let's say this one is 0 at a steady state, and let me see, L is steady state. DIA over dt is 0, that is 0. So basically, Vt is equal to RAIA plus what? K flux omega. Right? K flux omega. Also, T electrical is a K flux IA. Right? So when they add energy conversion, they know this, but those when they don't have it, just accept it. The electrical torque generated in the machine is going to be this much, right? Now let's replace the IA with a TE. Okay, so VT is going to be RA TE over K flux, right, plus K phi omega. Let's find omega m here. Let's find omega m here. It's going to be Vt over K flux, right, minus RA TE over K flux to the power of, right? Let's say we have a constant load here, right? You know, at a steady state, how much is this one? Machine is going to rotate at constant speed, right? It's going to get to some speed. So this one is 0. Basically, T electrical is equal to T amp, or T load. In this case, it's a T load, right? If T load is constant, this one also is constant, right? Now, if I want to control this one, let's say I'm not changing this part. Whatever I have here, I'm not going to touch it. This is my excitation circuit. Means the flux is going to be constant, right? So, if I don't touch here, what else I can change? Right? How to change it? Right? Basically, you can change this duty cycle, right? So you can control this one. Look at this duty cycle. If D is 0.5, how much is the V out? 0. The motor is not going to rotate. If D is more than 0.5, for example, motor is going to go clockwise, for example, right? If D is negative, you are applying reverse voltage. It's going to go reverse, right? So it's a simple control system here. But this is the open loop. If you are going to go to closed loop, there is a block diagram for it. This is the last topic I want to talk about, and we finish it here. We want to have a closed loop control DC motor. See, you have your omega ref here, right? I want this machine rotate at 100 RPM or 200 RPM or whatever you want, right? So basically, I should have my feedback, right? I should measure the omega, the speed of the motor, right? Bring it here. Here I'm going to have a speed controller. A speed controller basically is a PI, or whatever you want, but the simplest one is going to be a PI, right? This one is going to give me the IA ref. So I measure the armature current and bring it back here also. IA. Another, here we call it current control. This one is going to give me the V control. Or D, you can call it D. I don't know, V control. V control this is basically the PWM generator, right? It's going to generate the pulses here, right? So whatever is here is going to go to S1 and S4, and the nut is going to go to now we have that H bridge, right? We call it H bridge, that one, right? This H bridge is connected to this DC motor, right? This DC motor is connected to the load and is rotating with omega. Basically, we sense this current, bring it here. We sense this speed right here. This is a control system with the internal current loop. So this is the internal current loop. You could get rid of this one if you want. If you don't want to have it in the internal current loop, you can get rid of it. But the problem is, old system they were like this. If you don't have this one, you don't have any control on the current. So you want to see the speed, right? Maybe you are very far from the reference value. You ask for a huge current. And this guy will go set up for that. What is the problem with the huge current? It's going to burn the H bridge, it's going to burn the motor, right? He said, when you have an internal current loop, he said, okay, how much current do you want? 200 amps. Oh, sorry, I can give you just 100 amps, right? Let's go slowly there, a steady state cannot be very high because at the end, you are not able to provide that. Let's say, for example, you want to go from this speed to this speed, right? You want to go from here to here. If you don't have an internal current loop, IA, for example, is going to be like this. You are stable here, right? Now, for example, this is 10 amps, for example, right? So what is going to happen? We said, boom, you are going to use here, and you're going to come back, for example, for this case, for example, you need 12 amps, right? But this one, if you look at the speed is going to be like this. Very quick, it's going to go here. The speed, right? The good thing is the response is very fast, but the bad thing is maybe you lose everything, right? Because of this one. Now, what the internal current loop does? See, here I didn't put it here, but usually there is a limiter here. Limiter here. And this is the IA there. I know how much is my limit here, how much I can send to this system, right? I can handle, for example, in this case, only 20 amps, right? What is going to happen when I have that one? It's going to be like, no, not here. You're going to go to 20 amps. See, the time is going to be longer. So if you look at the speed, it's going to go like this compared to this case, right? But it's safe because your current is limited. You are not passing the limit. So basically, you could get rid of this current loop here and run it, or you could have a current loop, which all of them they have a current loop now, to make sure you are not killing the rest of the unit here. Another application, I'll say this one also it's good to hear the name, of this thing. Two quick ones I'll say, and then we'll stop it. SVC, they call it a static var compensator. SVC. SVC is this. I'm not going to put the detail here. This is the inverter. The three-phase inverter, you guys know. But there is no value or anything. There is only capacitor here. SVC is a static var compensator. This guy is going to only inject the reactive power because he doesn't have a battery or any energy source to inject any active power. You have your transmission line here, and this one is connected here. This is a transmission line or distribution grid, right? You want to stabilize your voltage. When you have a big grid, maybe some points the voltage is too low. If you put one of this one here, it can inject reactive power to the grid and support, they call it voltage support. This one can inject or absorb Q to the system. And it's going to support the voltage here. For transmission line is very expensive. Think about it, this is 400 kV. Think about it. And usually there is a transformer, for those ones usually there is a transformer here. Because there is no switch can handle 400 kilovolts, you know what I'm saying? You have to have a switch, a transformer to bring down the voltage here. This is another application. The last one I want to talk about it is, I'm not going to put anything on the board. HVDC, they call it high voltage DC transmission line. You guys, you should let me tell you. Do you know why we use the AC for transmission line? Any of you knows anything about it? Why they use all this AC transmission line there? This transmission
You'd
line
have to have
there.
massive relay stations for DC.
Huh?
You'd have to set up massive relay stations for DC.
But DC breakers, they are more expensive and difficult to build, but that's not the reason.
Because the loss on the wire.
Because the frequency doesn't change everything.
What do you mean loss in the wire?
Loss. Because the average current is 0.
Actually, if it's DC, you know our DC is better than our AC, right? Because when the current is AC, there's a Hall effect. You know, the resistance, effective resistance is a little bit more than the DC. But in general, power loss is proportional to 1 over V square. Whatever is your voltage. You know, we can prove this one, but I'm not going to prove it. I just accept it. The power loss is proportional to 1 over V square. Right? All time. They have a, for example, they have a hydro dam, right? Hydro power plant. I don't know, it's where, for example. I don't know, we have a nuclear power in San Diego, right? Not San Diego, near Irvine. Now we need to send the power to Bay Area, San Francisco, right? So there is a long transmission line. I don't know how many miles, maybe like 500 miles, something like that, right? So it's pretty long line, right? If I'm going to send that one with a small voltage, low voltage, like 10 kilovolts, something like that, because the biggest generator they built is 11 kV. 11 kV was the biggest generator they had at the time. To reduce the loss, can I really increase the voltage? Yeah. If I have a transmission line, I have my generator here, right? I'll put the transformer here, bump it up, right? From 11 kV to 700 kV or whatever I want. Here I arrive to Bay Area, right? I put another transformer, bring it down, and here's our money load. Right? There was only AC transformers to do this one, right? If I had a DC generator, I cannot bump it up, right? Transformer, they don't work with the DC, right? DC power. They get saturated. So that was the main reason they used to use the AC transmission line. But nowadays, they call it HVDC, high voltage DC transmission line. With the existing, you know, with the advancement of power electronics, now they can, you know, boost the voltage. You have a boost converter, right? Yeah. Just boost it up. Just boost it up, you know. Put as many switches you want, you know, boost it up. You can have another one is like you have the DC to DC converters with the transformer in the middle, right? You will have a DC here, you make it AC, send it up, take it up and go there again, bring it back. But usually it's like a boost converter. They call it voltage multiplier. They call it voltage multiplier. Now if you type, you know, power electronics voltage multiplier, it's going to bring some of them in Google. Just type that one, you can see some of the circuits. Nowadays, with the advancement of power electronics, because, I forgot to say this one, because DC transmission line, they are more efficient than the AC transmission line. The problem at the old time, they didn't go there, it was this factor. With the AC, they can go up, with the DC, they cannot. If they had an option to go with the DC high, with the AC high, DC is better than AC economic-wise and power loss-wise. But because they didn't have this big advantage over the AC, so they went with the AC transmission. Nowadays, if there is a new line, not existing, think about it, there's a transmission line from San Diego to Bay Area, see how much is the price of that transmission line. They're not gonna take that one out and put the DC in, you know what I'm saying? Whatever is there is there. You're not gonna throw out that one and go with a new one. But if there's a new line, new thing they are gonna establish, they do usually study, and it happens, you know, between Canada and US, there is a undersea cable is DC. It's all DC. It's a huge, I think it's, I don't know how many megawatts is it, you can exchange power, you know, with the DC. Hopefully, this course was enough to give you a kind of idea of what power electronics, I don't know, application, control. You are not a design engineer, but if you want, you can continue this path to become one day, you know, power electronics design engineer. And hopefully you'll get a good job. So I'll see you Saturday night. Last year they were all